Okay, so this video is for Mr. G's topic 9.1 formative assessment. There's some problems here, and this video is to walk through the solutions to these problems. So we're starting off with the first set. We have numbers, let's see, maybe about 1 through 5 here, talking about this spring system that is in oscillation. We're given the mass right there. We are given the that it takes 0.75 seconds to complete an oscillation. And then we're told in number 1 that when time is 0 at the beginning, the mass that's attached to the spring is pulled 4 centimeters in the positive x direction. And so it's asking what are the amplitude, period, and frequency, which were kind of already given. We don't need to make very many calculations here. And so we remember that amplitude is the maximum displacement away from the equilibrium position. Equilibrium position is here, and it says that it's pulled 4 centimeters away from the equilibrium position, so that would be the amplitude. And we know that period is the time to complete one cycle, and we're given that. It says the mass takes 0.75 seconds to complete an oscillation, so there's our period. And then frequency, we know that frequency and period are inverses of each other. Frequency is 1 over the period, and so 1 over 0.75 is 1.33, and seeing as the original period is to 3 significant figures, so will the frequency be 3 significant figures. And you can use a number of different units for frequency. Hertz is common. You can say cycles per second, or even 1 over seconds. Of course, the IB uses negative exponents for 1 over, so that's 1.33 seconds to the negative 1. All right, number 2. Okay, so they give a specific time, 2.45 seconds, which is not an integral number of the period, it's just a random time that was selected. So basically it's asking for position, which would be x, as a function of time, which would be t. And on the data booklet, we do have 2 equations, actually, for position as relating to time. One is sine and the other is cosine. And the reason why we have 2 equations, like, well, which one is it? It actually depends on the starting conditions, but of course these 2 solutions, the sine and cosine solutions, I'm referring to them, they're equations. I'm using the word solutions, I'm jumping ahead of myself. They are the solutions for the differential equation that describes simple harmonic motion. But it's, well, which one is it? Because, you know, you'll get, we can figure out the angular frequency omega, we already have the amplitude, we have the time, but you get different values if you use sine or cosine. And again, just to be clear, for sine and cosine, since we're dealing with angular frequency here and not standard frequency, I don't really know like what else to call that. But since we are working with angular frequency, we are going to need our calculators to be in radian mode. But that still doesn't answer if we should be using sine or cosine, and again, that actually goes back to the starting conditions. We're actually going to be using cosine in order to figure out this position. The reason why we use cosine is when your initial condition displacement, when time is 0, when you begin at the starting point, the displacement is the equilibrium condition. And we see that right here, that it says that the mass is pulled 4 centimeters in the positive x direction before release, right? So we are not actually starting with the mass in the equilibrium position in motion. Notice I said in motion, because if the mass were in the equilibrium position and it were not in motion, then nothing would be happening. So it's the mass as it is at time 0 is not moving when time begins, but it is in the fully stretched position. It's at the equilibrium position. So that's, like I said right there, when the displacement is equal to the amplitude at time 0, we use cosine. The other condition is when the displacement is in the equilibrium position, or 0, at the beginning at time equals 0. And that's not the case here, so we'll be using the cosine equation. Let's proceed. One further step. In number 1, it asked for the standard frequency. It did not ask for the angular frequency. We will need the angular frequency. Let's get it. I'm going to cheat a little bit. 2 divided by 0.75. 0.75 is 3/4. 2 divided by 3/4 is the same as 2 times 4 over 3. That's 8 over 3. So 8 over 3 times pi seconds to the -1. I'm saying cheating a little bit. This way I'm dodging any issues with significant figures. So I'm going to sub that in for x equals x naught cosine omega t. So I substituted in our displacement, our amplitude from number 1, put in the angular frequency, and then put in the period. Not the period, 2.45 seconds. That's my bad. Let me fix it. Oopsie, glad I caught that. So that would be 4 times cosine of 8 pi over 3 times 2.45, not 0.75. In radian mode, gives me displacement of negative 0.42 centimeters. The original amplitude was in centimeters, so my answer is also going to be in centimeters. And the original amplitude was to 2 significant figures, and so I put my answer to 2 significant figures. Now, number 3 asks for the velocity at 2.45 seconds. There's actually 2 formulas that we can use here. If you look at the data booklet, you'll see that right underneath the cosine formula for position that we used is the derivative of that. The first derivative of cosine is negative sign. So if you look at the x equals x naught cosine omega t equation, the derivative of that would be that velocity is negative omega x naught sine omega t. So in other words, for the velocity versus time equation, we're going to be using the sine guy on the right. Now, that would make sense for figuring out the velocity as a function of time because we're given the time. However, we now also know the position at 2.45 seconds, and so we can use the velocity versus position equation. We figured out the angular frequency. That's 8/3 pi seconds to the -1. We know the amplitude is 4 centimeters, and we know the position at 2.45 seconds is negative 0.42 centimeters. I'm not going to write out this expression fully, but I will give you the answers for both approaches. If we use velocity versus time with the numbers that we have, we wind up with, we get negative 33 centimeters per second, 33.32674,859. So it says my calculator. If we use the velocity versus position equation, we get the same answer down to the thousandths place. Sorry, make that the hundredths place. But I don't need that many places. I only need 2 sig figs. Now, the velocity versus time expression gave us a hint that we should be considering a negative velocity. And of course, the velocity versus position expression is plus or minus because the displacement is squared in the formula. So if the displacement were positive or negative, it wouldn't matter because you're squaring it, and so the solutions for that situation will both be positive or negative. If we consider that at 2.45 seconds, the period is 0.75 seconds. So if we divide 2.45 seconds by 0.75, we get about 3 1/4. So meaning that it's about 3 1/4 oscillations, where the initial condition is that the mass is displaced positively already. So if it's completed 3 oscillations, it goes back to where it started. And if it then has about 1/4 of an oscillation back, that's not even half an oscillation, so it's going to be going back the other way. It's going to have a negative velocity. So yeah, our answer for number 3 is going to be negative 33 centimeters per second. Number 4 is asking for the acceleration at 2.45 seconds. We don't have an equation for acceleration versus time. We do have the defining equation for SHM, being that acceleration is negative omega squared times the displacement. Thankfully, we have the displacement that's the answer to number 2. Keeping in mind that you square the omega before you apply the negative, otherwise it would have the negative omega in parentheses. So we have the angular frequency, we have the displacement, let's do the math. And for a solution, I get 29, and since the displacement is in centimeters, that's going to be 29 centimeters per second squared. And probably the simplest question, what is the force acting on the mass at 2.45 seconds? Some classic Newton's second law, sigma F equals ma. And it doesn't say anything about any damping force or frictional force, it's just simply the spring acting. So we know the acceleration, we know the mass. Now the force, if it's going to be in newtons, that's interesting. You know what? I'm going to need that acceleration in meters per second squared in order to get force in newtons. All right, let's figure that. So if the acceleration in centimeters per second squared is 29, then in meters per second squared, it would be 0.29. And seeing as how the acceleration is positive and the mass is of course positive being a scalar, that gives us a positive force as well, 0.44 newtons. Now, number 6, I don't actually have a solution set for this formative assessment, so I hope I'm right. But number 6 says that a mass is displaced 4 centimeters in the negative x direction, so that it's released. So it's released with maximum displacement with release at the amplitude condition from rest. It says released. Yeah, so like it's pushed back and released, not pushed, so it's not given any additional velocity. So its initial velocity is also 0. And it says, what is the phase difference between the two systems? Well, in terms of a cycle, if we're saying that the first, so this was the original mass, and so one cycle, of course, would be out and back. And so that's one complete cycle. So seeing as how this mass is halfway through that cycle on the other side of the equilibrium point, I would say that the two systems would be completely out of phase, would be 180 degrees out of phase, or if we're talking radians, that would be pi radians. Okay, so 1 through 6 is for that system with the spring, and then 7 through 9 seems to be about a car rounding a turn. Okay, so for 7 through 9, we actually have a circular motion question, which is topic 6, so that's a throwback to SL. It's connected, though, because anything that's in simple harmonic motion is also connected to circular motion. If something moving in a circle is also simple harmonic. I should say moving in a circle at constant speed, it's simple harmonic. So for number 7, it asks for the angular speed in radians per second, and so it actually gives us the angle in degrees, so we're going to need to convert 30 degrees into radians. Remembering that 180 degrees is pi radians, we can then set up a ratio to find that 30 degrees is pi over 6 radians, because 30 degrees is 1/6 of 180. So yeah, 30 degrees is pi over 6. And angular speed is omega. I think earlier I was referring to omega as angular frequency, but I see here they call it angular speed. But in any case, it's the amount of angle per unit time. It's angle passed per unit time. So we have pi over 6 radians divided by 2.5 seconds. And yeah, so pi over 6 divided by 2.5 gives us pi over 15, or if we simplify that, we get 0.21 radians per second for the angular speed. Now, so it gives us the radius. This is what is its actual tangential speed during that turn. And if we reach back to topic 6, 6.1 circular motion, we get that tangential speed is the angular speed times the radius. Well, we have the angular speed, that's why we did number 7. So we multiply times the radius, and we wind up with 7.3 meters per second. 7.4 depending on how you round. I actually used, I left the number in my calculator and then reused it in number 8, which gave me 7.33, but if I used the rounded 0.21 from number 7, I wound up with 7.35, which is 7.4 meters per second, but close enough. All right, angular acceleration is also called angular acceleration, and angular acceleration is also called centripetal acceleration, but that is the speed squared divided by the radius. And again, this is angular acceleration, not tangential acceleration, because the circular motion condition is that you are moving at constant speed. But anyway, we just found that speed. Let's square that and divide by the radius, and we get a angular acceleration of 1.5 meters per second squared. All right, next question set. Okay, so for numbers 10, 11, and 12, and 13, we're dealing with a spring, and another simple harmonic oscillating spring, but this time the mass is being released or being pushed really from the equilibrium position. It's given an initial velocity v naught, whereas the one earlier was starting from the amplitude position, the maximum displacement. So we know the mass, we're given that initial velocity of 6 meters per second. It says single cycle, so the period is 4.25 seconds. And so once the angular frequency of the system, that's the first equation for 9.1, that would be 2 pi over the period. And we wind up with an angular frequency of 1.48, I suppose, radians per second, or seconds to the negative 1 for number 10. Then 11, what's the amplitude, x naught, of the motion? Well, I know the initial velocity in the positive direction is 6 meters per second. And so if I use the equation, plus or minus the angular frequency times the square root of the amplitude squared minus the position or the displacement squared, that's squared, not x2, it's x squared, my bad, fix that. And then the velocity that we know is at the equilibrium position. And again, equilibrium position is when the displacement is 0. So when, why is my pen not working? Because I was using an eraser, go me. When x equals 0, then the speed is 6 meters per second. All right. And so if I put in a 0 for x, that just gets me v equals plus or minus omega radical amplitude squared, which if we just square root the the square root of the amplitude squared is just simply the amplitude. So we get that the speed is plus or minus the angular frequency times the amplitude, and amplitude is what we are looking for. And so I can say that our velocity is positive, and I can take the positive amplitude, so I'm going to take the positive version of this expression, pop in v, pop in the angular frequency, and just solve for the amplitude. And of course, meters per second divided by 1 over seconds, it gives us simply meters, which is what we're looking for. And that gives us a 4.06 meters. We get 4.05 if we actually use the rounded 1.48 for omega. I use the non-rounded answer that I had in my calculator so that I don't get an intermediate rounding error. It's not really that much of a big deal. So there's our amplitude. Now we need position as a function of time. So where is the mass at 10 seconds? And of course we have two expressions for position or displacement as a function of time. There's a sine equation and a cosine equation. And again, you got to figure out which one you're going to use. Now, we know that we're talking about at the beginning at time 0, our displacement, our position is 0. It's in the equilibrium position. So we know that the sine of 0 is 0, and the cosine of 0 is 1. So at time 0, then we get, using the sine expression, we get that x equals 0 because the sine of 0 is 0 and anything times 0 is 0. But the cosine of 0 is 1. So at time 0, if I use the cosine equation, that gets me the cosine of omega t is 1. So that would get me that the position is at the amplitude. Like we're starting at the the initial position at time 0 is at the amplitude position, the maximum displacement. That's not the case. If you look at that, at time 0, we're starting in the middle in the equilibrium position. So we do not want the cosine expression. We want the sine expression in this case, which is opposite from where we started with the first question, where at time 0, the mass was at the amplitude position, the maximum displacement position. So that's why this is a separate question. And we know the amplitude from number 11. We know the angular frequency from number 10, and it said 10 seconds is our time, so let's figure that out. And so we wind up with 3.2 meters for our position, and I'm using radian mode since we seem to be working in radians. Sorry about the coughing. Anyway, 3.20 meters. Okay, so for 13, we need the velocity as a function of time. we have two expressions for velocity, just as we have two expressions for position or displacement. We have a cosine expression and a sine expression. Now, considering that at time 0, going back to the initial conditions, at time 0, we do have a v naught. The mass is actually in motion, as opposed to earlier when for number 1, etc., we had a mass that was displaced to the amplitude position, but it was not moving at time 0. So now we actually have the other case. We have that the mass is in the equilibrium position such that when time starts, the displacement is 0, but when time starts, velocity is not 0, velocity is at a maximum. So what does that mean for our expressions? Well, we're going to want, again, time being 0. Again, and I know time is not 0, it's 10 seconds, but I'm choosing my expression here, whether I'm going to be using cosine or sine. And when time is equal to 0, I want a non-zero velocity, right? So I know that the cosine of 0 is equal to 1, and the sine of 0 is equal to 0, which, if I were to use this equation, that would say that at time 0, then the velocity is also equal to 0, which we know not to be the case. At time 0, for this case, the velocity is at a maximum, so I'm not using the sine expression, I'm using the cosine expression. Now again, to be clear, I'm not actually using v is equal to omega x naught. That's actually the maximum velocity. It's asking what is the velocity at 10 seconds, not at 0 seconds. So I kind of like this worksheet because number 13 touches on the things that we previously solved for. We solved for omega, we solved for the amplitude, and now we will be using those things in this expression. Let's get ourselves a final answer. And we wind up with a velocity of negative 3.7 meters per second, which actually makes sense. Let's think about the time of 10 seconds, especially considering the period of the system is 4.25 seconds. If you divide 10 by 4.25, that gives you about 2 1/3. So that's like 2 1/3 cycles. So 2 1/3 cycles, there's 1, 2, and then a third. So half a cycle would be out and back. So a third of a cycle would be out and maybe about to right about there. So at that point in its cycle, it is on its way back, but it hasn't achieved the highest velocity of 6 meters per second. So our answer of negative 3.7 meters per second kind of makes sense because the mass is on its way back to the equilibrium position, but it's not yet at the maximum velocity. This also reassures me that I'm working in radians because when I solve for the same expression in degrees, I get almost positive 6 meters per second, which is what the velocity would be if it was moving to the right, maybe towards the completion of one cycle, which is not where 10 seconds would be. So there you go. All right, we have, I think, 2 more problem sets, 14 through 19 and 20 through 22. I'm going to see if I can knock this out within the 30-minute time limit. Let's see. So for 14 through 19, we have a displacement versus time graph. We know the mass is 4.5 kilograms, and it says in the problem that it's undergoing simple harmonic motion. From the graph, we can ascertain the period. We can see that one cycle does complete in 3 seconds. We can also see that the amplitude of the system is 1 meter. Recall that omega is 2 pi over the period. I got that off the reference table. Knowing the period, I can get that the omega is... For now, I'm going to leave it in terms of pi for simplification and to avoid rounding errors. So that's 2/3 pi seconds to the negative 1 will be omega. Now, that's not just a fun fact. I'm actually going to need that in order to answer 14, total energy of the system. From the reference table, I see that total energy for a simple harmonic system is 1/2 the mass times the omega squared times the amplitude squared. I have all of these things, so I can just calculate total energy from that. Seeing as all the data is to 2 significant figures, that gets me 9.9 joules. Just as a side note, where am I getting joules from? We have, remember that the fundamental units for a joule are kilogram meter squared per second squared. Kilograms is brought by the mass, the meter squared is brought by the amplitude squared, and the 1/second squared is brought by the omega squared. So yeah, it's a joule. Position versus time again. I'm going to be using the sign expression because at time 0, I can see that the position is 0. So if we let time be 0, the only way I'm going to get a position of 0 is if I use the sign expression, because the sine of 0 is 0. And of course, the cosine of 0 is 1. So I do not want this one, I want this one. Now, using that expression, we wind up that x, the displacement, the value that we get is simply 1, not negative 1. I'm assuming that this expression assumes that the initial displacement of the particle is not going to be in the negative, but rather in the positive. If the graph instead looked something like this, kind of going that way, then yes, the answer to 15 would wind up being positive 1 at 3.75 seconds. But in 15, I'm pursuing a solution answer. Honestly, I could just read the graph, find 3.75 seconds, and see what is the actual displacement of the particle. At 3.75 seconds, I can see that the displacement is negative 1 meters. I can also see at 3.75 seconds that the particle is at its maximum displacement. It says that this is a mass attached to a spring undergoing simple harmonic motion. At maximum displacement, all of the energy is stored as potential energy. So I already solved for the total energy of the system being 9.9 joules. So at 3.75 seconds, the potential energy in the spring is 9.9 joules. And then at 17, it says what's the velocity at 3.75 seconds? And I could use a velocity versus time expression, but again, I can see at 3.75 seconds that the particle is at maximum displacement. When at maximum displacement, the velocity is always 0. The acceleration, while the velocity is 0 at maximum displacement, the acceleration is at a maximum. But this I can actually calculate. And we wind up with a positive number of 4.4 meters per second squared. I would expect that it's positive because now that the particle has displaced to its maximum negative displacement, it's going to be on its way back to the equilibrium position. So if it's at its maximum negative displacement, it's on its way back, meaning that it's on its way up in the positive displacement direction. So yeah, that acceleration would come out as a positive number. And then number 19 is some classic F equals ma action. Now that I have the acceleration and I know the mass, I can get use F equals ma to get the net force. There's no damping force or any other external forces, so it's just F equals ma, which to two significant figures yields me 20 newtons as the force. Positive force because it's a positive acceleration. Last but not least, we have a pendulum in Moscow for numbers 20 through 22. So 20 wants to know the length of the pendulum, which we can actually figure out based off of the period, which we need to figure out from the graph. The graph is displacement in millimeters, that's what it says, versus time in seconds. So if I can find one cycle of time in seconds, I can figure out the period. There's one cycle. The one cycle goes from 0.5 seconds to 6.5 seconds, giving me a period of 6 seconds. Get L by itself, divide both sides by 2 pi, square both sides, and multiply by G. We have G from the problem set. It says that it's 9.84 meters per second squared. Meters per second squared, not meters per second. Epic fail. That's super unfortunate. I never make any mistakes. My math is always completely perfect. Right. If you're wondering about the 9.81, by the way, it just so happens that Moscow is 9.84. Maybe they're built on a big giant rock. I don't know. And it's two significant figures because even though the G value is to 3 sig figs, the values on the graph are 2 sig figs. For 21, we can use the same formula that we used for 20. And for 21, I get 1 meter. And so 21 is pretty easy considering we did number 20. Now let's do 22. That should be easy peasy. Mercury, what the what? So Mr. G's getting cute. He's throwing back to 6.2, but we have an equation there. It says the original pendulum, that had a length of 9 meters, but I'm going to have to figure out G for Mercury. So GM over R squared. Where are big G's on the fundamental constants on our data booklet? Tricky, tricky. 2,440 kilometers. We want to put that in meters. The reason why we want meters is because meters is used in big G. So let's figure out little g based on that. And when it all works out, we have a Mercury period of 9.8 seconds. And that is the last question. There are 2 more questions. In 10 seconds, 24 reaches back to topic 2.3. Thank you, and I'm done.